In Chapter 3, we were looking at graphing and working with quadratic functions. In Section 4.1, we're going to look at more nonlinear functions that are not quadratic functions. Some may be quadratic, but most of them probably are not. We're going to be looking at polynomial functions. A polynomial function of degree n and the variable x can be represented by this function right here. So this is a polynomial function where a sub n is a real number assigned to x raised to the n power and so forth and so on. So what we see is we have a function of x where x is raised to positive integer powers. This first term for the highest power of x is called the leading coefficient. The highest power on x is called the degree of the polynomial. The domain of any polynomial function is all real numbers, and its graph will be a continuous smooth curve without any breaks or sharp edges. If we have a function f of x equals 10, the degree on that would be 0 because we don't have an x. Or we could write times x raised to the 0 power. What is x raised to the 0 power? Well, anything raised to a power of 0 is 1. So this would be like 10 times 1. So the degree is still the power on x, it's just that power happens to be 0. So if you have a constant function, the degree is 0 and the leading coefficient would be that constant. If I have a linear function like I have in g of x, the degree would be 1 because the assumed power on x is 1 and the leading coefficient here would be 2. It's the constant that the highest power of x is multiplied by. On h of x, we have a quadratic function because the highest power on x is 2, which means the degree is 2, and the leading coefficient will be 3 because 3 is the constant that the highest power of x is being multiplied by. On k of x, the degree of this polynomial function is 6 because 6 is the highest power on x, and the constant that x to the 6 is being multiplied by is negative 1/2. So here we would say the leading coefficient would be negative 1/2. These polynomial functions have absolute and local extrema. Absolute just means absolutely the highest or absolutely the lowest. Local means that it could be just a relative or a localized maximum or minimum value. For this function in figure 4.4, we have an absolute minimum value of negative 6 right here at x equals 2. There's no absolute maximum because these n's go up forever. On figure 4.5, we have an absolute maximum of 12.7 right here. This absolute maximum can also be considered a local maximum. Absolute can pull double duty as a local. So every absolute max is also a local max, but not every local max is considered an absolute max, because here's a local maximum value at 2.25, but it's not the absolute because there's one that's higher. Do you see the difference? Maximum just means you have a high point, a localized maximum value. Here would be a localized minimum value at x equals 1. We have a local min of negative 3.1. There is no absolute minimum value because this graph goes down to negative infinity. Maximum and minimum values that are either absolute or local are called extrema. Extrema is another word that encompasses both maximum and minimum values. A function may have several local extrema, but at most only one absolute maximum and one absolute minimum. Absolute means that it is the one. There can only be one of those, but it can have a lot of local. So for this graph, we have an absolute maximum value of 11. That's also our local max. We have a local min right here at 3.5. We have a local min right here at about 3.5 at x equals 0. But it's not an absolute min because this graph goes down to negative infinity. So we would say we have an absolute maximum of 11 at x equals negative 2 and 2. Here we just have a local minimum of, let's say, 3.5 at x equals 0. There is no absolute minimum value here. And I've already explained in plain English what absolute and local extrema are, so I don't feel a need to go over that again. In example 1, we're told that the graph shows the monthly average high temperatures at Daytona Beach. We're asked to identify the absolute maximum and minimum values. What would be our absolute maximum value here? It would be this point right here at 90. And then the absolute minimum, it's not at 70 because 70 is at this point. This one's a little bit below 70. Do you see that? We'll call that 69. And this would be degrees Fahrenheit. What about any local maximum values. Do we have a local max? Our local max is this point right here. In order to be a maximum, it has to be the highest point in some open interval around that point. This point right here would be a local minimum. It's not a maximum because there's points that are immediately to the left of it that are bigger. Remember, I said local and absolute can pull double duty. Every absolute is a local, but not every local is an absolute. Absolute trumps. But if it is an absolute, it's also a local. In example 2, we have another graph. We're asked to use the graph to estimate the local extrema and absolute extrema. So for this problem, I would have a local maximum value where? Right about here. This would be the local maximum. And each of these tick marks here is a unit of 3, so it looks like that's going to be at maybe 2.5. Do I have any other local max? No. What about local mins? I have a local min. I'll do it in blue. I have a local min right here because this is a dip down, and right here because this is a dip down. Do y'all see that? So I have a local min at 2, and right here that point is at negative 12. My answers here are the y values. The maximum and minimums are the y values. Where they occur are the x values. So where's my absolute maximum? Do I have any? What about my absolute minimum? That would be at negative 12, this point right here, because that's the absolute lowest point. So even though I have 2 local minimum values, there's only one absolute minimum value. For example 3, we're told the monthly average ocean temperature in degrees Fahrenheit at Bermuda can be modeled by this function right here, where x equals 1 corresponds to January and x equals 12 corresponds to December. So the domain for the function is every month from January to December, so every day between January and December, so that's from 1 to 12. In part A, we're asked to graph this function using this window. These are the values for the x's. This is our x min, our x max, and our step. And this is the values that we want to use for the y on the window. And then we want to use this to estimate the absolute extrema and interpret the results. So we go to our calculators, and when you hit y equals, you're going to type in this function that you see right here for f of x. Then you're going to hit window, and you're going to set your window to accommodate these values, 1 for the min, 12 for the max, 1 for the step for the x's, and then 50, 90, and 10 for the y's. And then when we hit graph, we get this picture right here. In part A, when we're asked to graph the function, this is what the graph is going to look like, where this point right here, 1 corresponds to January, and then 12 corresponds to December. Part B asks us to estimate the absolute extrema. So it looks like we have an absolute minimum value somewhere here and an absolute maximum value somewhere there. How we do this on our calculator is by using the maximum and minimum finder on the calculator. That's going to look like this. We go to our calculators, and right above the trace button we see calculate, so we're going to hit second, calc, and let's find the minimum value first, so we hit number 3. Then we want to move this cursor over close to the minimum value. So you're checking your y's. If your y's start getting bigger, you know you're to the left of it. Then you want to pick a right bound, so we want to go slightly to the right of the minimum value. And then when you hit enter again, it's going to say, well, here's a guess. Do you want the guess? No, I want the actual minimum value. And this gives us the minimum at this point right here. So it looks like we have a minimum value of 61.5 degrees in early February, because remember the integers correspond to the months. So we have a minimum of 61.5 degrees Fahrenheit in early February. That corresponded to this value. What was it? 2.01 and 61.5 on the graph for the minimum. So this would be our absolute minimum. To get our absolute maximum, we're going to hit second, calc, and now we select the maximum value, number 4, and we have to move our cursor back over towards the maximum value. We want to stop somewhere slightly left of the maximum value, so I'm going to stop here, and then we need a right bound. We need a right bound, so we go slightly right of where we think the maximum value is, and then once again we hit enter again because we don't want the guess for our answer. We want this answer right here. So it looks like we have a maximum value of 82 at about the middle of July. Notice these points where the minimum and maximum values occur Those are turning points. It's where your graph changes from decreasing to increasing. Those are going to become very important in this next section, so I'm going to go ahead and mention them now. It's where your graph turns directions from increasing to decreasing or decreasing to increasing. Or we're also interested in different types of symmetry with polynomial functions. A function is said to have even symmetry if you were to fold this graph in half along this y-axis, and the left half and the right half would meet up. So this right half would lay exactly on top of this left half of the graph, meaning if I folded the graph in half along the y-axis, the left and the right would match up. All of these functions here have what we call even symmetry if they're symmetric with respect to the y-axis. That leads us to the discussion of an even function. A function f is said to be even if you have a point xy on the graph and there's also a mirror image at negative xy. We use this fact to help us if we're looking not at a graph but at a polynomial. We can tell if that polynomial is even or not by replacing x with negative x and see if we get the same function back. If you can replace x with negative x and have the exact same function values, the same y values, then your function is symmetric with respect to the y-axis and it's even. Another type of symmetry we have is called odd symmetry. This is when we have symmetry with respect to the origin. When you have symmetry with respect to the origin, it means that you could rotate this graph 180 degrees or flip it upside down and you have the same picture. So imagine rotating this picture. I can't actually rotate it, but imagine if I flipped it upside down, would my graph have the same shape on all of these graphs? If you've printed out the notes, just turn your paper upside down and don't flip it over. Just rotate it 180 degrees. And that's called odd symmetry. You have odd symmetry if your graph is symmetric with respect to the origin. To determine if you have an odd function, what we want to do is if we replace x with negative x, we get not the same function back, but opposite functions back. So an odd function is symmetric with respect to the origin, and you get the opposite function back. So if you replace x with negative x, and you get the opposite y value, you have an odd function. All of the O's go together, odd, opposite, and origin, because they're symmetric with respect to the origin. That's one way that you can keep it straight. Odd functions have opposite y's and they're symmetric with respect to the origin. Even functions, you get the same function back and they're symmetric with respect to the y-axis. If you have polynomial functions, all you've got to do is check the powers on x to see if you have an even or odd function. So if all of the powers on x are odd and you don't have a constant term, then you have an odd function. If all of the powers on x are even and you have a constant term or not, then you have an even function. In example 3, we're asked to identify whether f is even, odd, or neither. So we're checking to see what happens when what happens to the y's when I look at opposite x values. So here I have x equals negative 2 and I get 8. The opposite of negative 2 is 2, and I end up with the opposite y. So I'm thinking this is probably odd. But I've got to check all the points to make sure. So I have a point at negative 1, 3, and then 1, negative 3. The y values did change, and the 0 is 0. So this is an odd function because the y values are opposite for opposite values of x. The opposite x values give me opposite y values. Remember, y is equal to f of x. On B, is this function even, odd, or neither? Why is it even? WRT is my abbreviation for with respect to. It just saves some writing. This function's even because it's symmetric with respect to the y-axis. On C, is this function even, odd, or neither? Well, one way to check algebraically is we're going to replace x with negative x, and that's going to give us 3 times negative x to the 4th plus 7 times negative x squared minus 1. What happens when you raise a negative to a 4th power? It's positive, so this stays 3x to the 4th. What happens when you square a negative? It stays the same sign, and then minus 1. This is my original function, so because f of negative x is equal to f of x, this is what? Even. On part D, we're asked, is the square root function even, odd, or neither? Well, remember, the square root function looks like this. F of x equals the square root of x. To check and see if it's even or odd, I'm going to replace x with negative x. When I do that, that gives me the square root of negative x. Is this the same function that I started with? No. So we know it's not even. Is this the opposite of what I started with? It's not the opposite of what I started with, because the opposite of what I started with would have been negative square root of x. F of x was the square root of x. So because it's neither the same nor the opposite of what I started with, I say this is neither even nor odd. The square root function is neither even nor odd. And this wraps up section 4.1.